Hi, I'm Timothy Brusella, and today I wanted to do an example illustrating the first derivative test for my business calculus class. I have written down a list of the steps for the first derivative test, and we'll use those steps as we go through the following example. Here's the function f of x. F of x equals 2x to the fourth minus 16x cubed plus 7. They want us to find the intervals on which the function is increasing, the intervals on which f of x is decreasing, and the local extrema. For increasing, decreasing, and local extrema, we're using the first derivative test. So let me write this problem down. F of x is equal to 2x to the fourth minus 16x cubed plus 7. First thing we'll do, our first step, we're going to find f prime. So that would be an 8x cubed minus 48x squared. And we want to know, where is f prime equal to 0? Where is f prime undefined? We're finding those critical numbers. So first of all, set f prime equal to 0. And both of those terms are divisible by 8. So we have a common factor. We could take out an 8x squared. That'll leave me with an x minus 6 inside the parentheses. So where does 8x squared equal 0? Where does x minus 6 equal 0? It looks like we're getting two different critical numbers. First of all, when x is 0. Secondly, when x is equal to 6. These are my critical numbers. First of all, found the derivative. Second, we set it equal to 0. Third, we ask ourselves, where is f prime undefined? This is a polynomial function. Polynomial functions are defined for all real numbers. So f prime is always defined. That's nice. Polynomials are really nice because when you're trying to determine where is f prime undefined, it's never. F prime is never undefined. So we only have two critical numbers, 0 and 6. And a word of warning on this third step, where is f prime undefined? In that event, what you're looking for really are, you have to be careful with the functions involving square roots and the rational functions where you have variables and denominators, because you certainly don't want your denominators to be 0. Step number 4, we're going to label our critical numbers on a number line. There's my number line. Now I have to label 0 and 6. I'm going to be looking at the sign of f prime, so I'm making a little note here. I'm looking at the sign of f prime. I labeled the critical numbers on a number line. Now step number 5, we're going to choose a number in each interval and test f prime. So here we are, step number 5. We have to choose a number to the left of 0. I'll test -1. I'll choose a number between 0 and 6. I'll test +1. And finally, choose a number to the right of 6. I can use any number I want to, and it's easy for me to cube 10. Oh, that motion detector cut out the lights here in this room. I guess I need to move around more. So to the right of 6, I'm going to test 10 because that's easy for me to plug into. Here we go. Plug in -1 into f prime. Remember, f prime is 8x cubed minus 48x squared. Plugging in -1, we'll get f prime is equal to, that's a negative 1 times 8, that's a negative 8. Negative 1 squared is 1 times a minus 48 is just a minus 48. The exact value doesn't matter. All that matters is positive or negative. F prime is negative. F prime is negative. That means the function is decreasing. So, decreasing. Now, plugging in 1, we'll get an f prime equals, that'll be an 8 minus 48. Oh, that is also negative. Here we said it was negative, decreasing. To the right is 0. It's also negative, so the function is still decreasing. And finally, plugging in 10. 10 cubed is 100, so we have 800. No, 10 cubed is 1,000, so we have 8,000 minus 10 squared is 100, so 8,000 minus 4,800. That's positive. Finally, we have an interval over which the function is increasing. When the derivative is negative, the function is decreasing. Here we had 2 consecutive intervals over which the function is decreasing. And then to the right is 6. When the derivative is positive, the function is increasing. So let's summarize what we have here. Increasing, decreasing, local maximum, local minimum. Okay, realize that the function is increasing when the derivative is greater than 0, so the function is increasing on the open interval from 6 to infinity. Now it's decreasing when the derivative is negative, and we can't say from negative infinity up to 6. We have to break it into 2 situations. It's decreasing when the derivative is less than 0. At 0, f prime isn't less than 0, it's equal to 0. So we have to write from negative infinity up to 0, comma, from 0 to 6. Local maximum. A local maximum occurs when the function is, a local maximum occurs when it's increasing to the left of the critical number and decreasing to the right. That doesn't happen up here. So there is no local maximum. We do have a local minimum though. The local, that's when a local maximum occurs. Let me make a note. Here's when a local minimum occurs. It's decreasing and then it starts to increase. So that's when we have a local minimum. And we have one at 6. And there's several different ways you can express local minimums. They may want you to give you the x value at which the local minimum occurs, or they may want you to find the ordered pair. So I'm writing it as at x equals 6. And looking here at the problem, remember going back to the problem, we've determined when it was increasing. We said it's increasing from 6 to infinity. It's decreasing from negative infinity up to 0. Use a comma to separate those intervals, comma 0 to 6. And finally, which of the statements is true? The function has a local minimum at x equals 6. The function has a local maximum at x equals 0 and a local minimum at x equals 6. That's certainly not it. There's no local maximum. It has a local maximum at x equals 0, a local minimum. Looks like it's response A. We have a local minimum at x equals 6. So, in summary, to use the first derivative test, you find f prime. You determine when f prime is equal to 0. You determine if f prime is ever undefined. You label those numbers that you just found on a number line, testing intervals. If f prime is negative, the derivatives, the tangent line's falling from left to right. That means the function is decreasing. If the derivative is positive, then the tangent line is rising from left to right. That means the function is increasing. And then we use the information on that number line to state increasing, decreasing, local max, local min. Once again, this is Timothy Priscilla doing a little business calculus for my Math 1325 class. Bye-bye.